Okay, so this topic is about neutron cycle. So what is a neutron cycle? It involves the birth of a neutron and the death of a neutron. The birth of a neutron is basically how a neutron is produced, and the death means how it is converted, uh, how it is absorbed by the fuel and takes part in another fissile reaction, or it is leaked from the core and it is out of our consideration. So it just escaped. So this cycle deals with how a neutron is born and how it goes through different stages and then takes part in another fission reaction. So when we do fission reaction, we know that neutrons have two types of neutrons that are thermal neutron, and then we have fast neutron. And in fission reaction as a fuel, we use uranium-235. Now, this uranium-235 is not all part of the core. Basically, it actually have a very small part of the very small portion of the whole fuel rod. So basically, the fuel rod is consists of uranium-235 and 238. And the percentage of 235 is called enrichment, and the remaining part is uranium-238. So in the core, in the fuel rod, we have both types of isotopes of uranium. Now, in fission reaction, only uranium-235 actually takes part, and it is with the help of thermal neutrons. Okay, and what is a thermal neutron? A thermal neutron have less energy than 1 electrovolt. And the first neutrons have energy more than 0.1 mega electrovolt. That means they're very fast. Now, these first neutrons usually don't take part in fission reaction, but they do to a very little extent, and we will study about this later. But the neutrons in the mid-range, in between these two energy states, are called epithermal neutrons. So we will also deal with this epithermal neutron in this cycle. Okay, so let's begin. So for example, suppose in the beginning we have n number of fast neutrons. So what happens when neutron, this is a thermal neutron, this thermal neutron reacts with uranium and it transforms into barium and krypton and 3 neutrons and some energy, and this 3 neutron is fast neutron. So to make them available to fissile with another nearby uranium, it needs to be converted into thermal neutron. Okay, so here at the initial phase, the neutrons are fast neutrons, and in the cycle we will see how this fast neutron is converted into thermal neutron and taking part into another fissile reaction. So in the beginning of our reaction, we have n number of neutrons. So here this is our n. We need to go. Okay, so this is our n number of reaction. Now what happens? These n reactions, these n neutrons come from thermal fissile reaction, but there are and first they are fast neutrons, and the thing is they have more cross section with uranium 238. Cross section means the probability of reaction. So some of these fast neutrons react with uranium-238 and releases some more fast neutrons. So the the portion of the fast neutron react with uranium-238 and then it creates some other fast neutrons, so that total number of fast neutrons is now increased. So this factor is called fast fission factor. So this fast fission factor, we have these fast fissions and some part of it react with uranium-238 and some other fast neutrons come here. We have these previous fast neutrons and then you have newer fast neutrons. So we have now a new number of fast neutrons. And this factor is represented by this. So this is a ratio, that is the number of fast neutrons produced by fission with neutrons of all energies. Neutrons of all energies, that means here this n part, this was produced by thermal neutrons, right? And this part is responsible for fast neutrons, right? So these neutrons are produced by neutrons of all energies, whereas this n was only for thermal. So their ratio is this ratio. This is fast fission ratio. Okay. Now we have the second part. Okay. So what happens after we have this? Now at the beginning phase, we have this number of neutrons. Now what happens? Some of the neutrons, they're very fast and they get out of the core. That is called leakage. So suppose you have this number of neutrons and some of it got leaked. Okay. So and now you have the neutrons you have here, they are not leaked. They are non-leakage. So this factor is called non-leakage factor. So this factor is represented by P8. So the number of fast neutrons which remains in the core divided by the number of fast neutrons produced by fission with neutrons of all energy. That means what you had before and what you have after, their ratio. The ratio of after by before. So this is our first non-leakage factor. Okay. Now this non-leakage neutrons in the core starts slowing down. Now, why do they slow down? Because we have our ultimate goal is to slow them down to turn them into thermal neutrons, and we do it by use of moderators. So we can use different kinds of moderator. For example, H2O, heavy H2O is a good moderator. So moderator absorbs the energy from fast neutron and turn them into thermal neutron. Remember that we had thermal neutrons and we have fast neutrons. This middle part is called epithermal. So as the neutrons are slowing down to thermal neutrons, so in this mid journey some of the neutrons are absorbed by the core, which is called resonance absorption. So they start to slow down and some of them are absorbed, and then finally the remainings are slowed down totally to thermal level, which is explained here in this formula. Now we have the thermal neutrons. Now some of the thermal neutrons are leaked again. So you had these thermal neutrons and they get out of the core, and now this is the thermal neutron you have in the core. So thermal non-leakage factor PT. And in the later part, thermal utilization factor. So you have this neutron in the core and they are now to be absorbed by the fuel. But unfortunately, in the core, we have some other materials. other than fuel. So that can be other things like mentioned here, construction materials, water, boron dissolved in water, control loads, and etc. So you you need only the neutrons that are absorbed by the fuel, and the neutrons that are absorbed by the other materials, they are out of our consideration. So only this part is absorbed by the fuel. So this ratio is called thermal utilization factor. So the number of the portion of the neutrons that is actually utilized by the fuel. Now the last part is you have this number of fuel that are absorbed, sorry, this number of neutrons that are absorbed by fuel, but not all of them can actually fissile. Only a part of them fissile. So this ratio is called neutron yield per absorption. So the okay, so suppose this number is actually fissiles, and after fissiling they are creating a new number of fast neutrons, right? Like in the beginning phase we had one neutron and it hit uranium and it created three other neutrons, right? So this neutron was thermal and these three neutrons were fast. So here the incoming these neutrons, the part of these neutrons take part in fissile reaction and they create fast neutrons. So the ratio of the newly created fast neutrons to the number of the thermal neutrons that actually took part in fissile is called neutron yield per absorption. So you can see the formula from here. So this part is the date of this thermal neutrons and the birth of this fast neutrons, and these three fast neutrons will continue its life going through the cycle, repeating the cycle again. Okay, now we have a multiplication factor. Multiplication factor is basically what the number of neutrons you had in the beginning of the cycle and the number of neutrons you have at the end of the cycle. So if you take this example, we have three neutrons here after the end of the cycle, and in the initial phase we had only one neutron. So here multiplication factor is 3. Now what happens is, why multiplication factor is important? If multiplication factor is less than 1, if it's less than 1, the chain reaction will not sustain, right? Because now you have one neutron, and if the multiplication factor is less than 1, you won't have any neutron left to continue the reaction. So this is called subcritical. And if you have greater than 1, like in this case we have multiplication factor of 3, this fissile reaction will self-sustain, but this will become uncontrollable. If you remember, when a neutron hits an uranium-235 atom, it creates 200 electronvolts each neutron, and when these three neutrons will hit other three uranium atoms, it will create another 200, 200, and 200. So that is total 800 electronvolts. And if this goes on, like a chain reaction will keep going on, right? So the amount of energy will keep increasing at exponential rate, and that high amount of energy will become uncontrollable by the infrastructure. So is multiplication factor greater than 1 desirable? Yes, it is. If you want to build atom bomb, you need to keep the multiplication factor greater than 1. But for power generating factor, we need to have control over the power we are generating at a constant rate. At the same time, we want the reaction to self-sustain. So, so in that case, we have to keep the M 1 or closer to 1. Okay, when the M is greater than 1, it is called supercritical. Okay, and this, when M equals 1, the unity, we call it critical condition, and that is the most desirable condition in your nuclear power plant. So when the critical multiplication factor is 1, your power is not increasing at exponential rate. It is under control, and it is also self-sustaining. So this is the most desirable condition. So this is our multiplication factor. And now, how we can find the multiplication factor? This is a ratio of what we have in the beginning, at the end of the cycle, and what you had in the beginning of the cycle. So we started with n and we ended with this. So if we make a ratio of the later versus initial, we will get this formula, and there are only 6 terms. So this is why it's called 6-factor formula. So this was all about neutron cycle. Goodbye.